Here's a tricky problem about averages. It starts by telling us that the sum of the integers in list S is the same as the sum of the integers in list T. So let's write G for given, sum S equals sum T. Then it asks, does S contain more integers than T? So we should write question, does S have more integers than T? And this is a data sufficiency problem, so to keep track of the answer choices, we should write our DAPSE grid. The first statement tells us that the average arithmetic mean of the integers in S is less than the average of the integers in T. So we should write 1. Average S is less than average T. To find out if this statement is sufficient, we need to see whether it implies a certain answer to our question. So we need to figure out whether this information is consistent with the answer being yes, and whether it's consistent with the answer being no. To get at this, let's try to find examples. We want to see if we can find a yes example and a no example. So let's try to pick a yes example. The first thing we know is that the sum of S equals the sum of T. So why don't we say that the sum of each of these lists is 30. 30 is a good number to pick because it's divisible by a lot of simple numbers like 2 and 3, and that's going to be useful later when we have to compute the average. And given that we're trying to build a yes example, we want S to have more integers than T. So let's say that T has just one number, whereas S has 3. The single number in T has to be 30, since the sum is 30, and for list S we have a bit more latitude, since there are 3 numbers, but the sum still has to be 30, so let's keep it simple and say we have 3 instances of the number 10. Then the average of S also has to be 10, and for list T, the average is going to be 30. Since 10 is less than 30, this meets the requirement that average S has to be less than average T. Now let's try to find a case where no, S does not have more integers than T. So let's say that S is the one that has one number, and T is the one that has 3 numbers. As always, the sum of S has to equal the sum of T, so let's say that in each case, the sum equals X. For list S, this implies that the solitary number is X, and that the average is also X. For list T, things are a little bit less clear, but we do know that with a sum of X and with 3 terms, the average is going to have to be X over 3. To find a possible numerical value for X, we have to remember that statement 1 tells us that the average of list S is less than the average of list T. And we've just seen that the average of list S is X, and the average of list T is X over 3. This is saying that the entirety of X is less than 1/3 of X, which seems paradoxical. The only way this is going to work is if X is a negative number, and you can see this algebraically if we subtract X over 3 from both sides. The left side becomes 2/3 of X, and the right side is just 0. And this last line, of course, implies that X is less than 0. So we can choose X to be any number as long as it's less than 0. To keep our no example similar to our yes example, why don't we just say that X is negative 30? And if X is negative 30, the average of list T, which is X over 3, is now going to be negative 10. And to keep T simple, why don't we say that its 3 members are all negative 10? So now we found both a yes example and a no example. which means that statement 1 fails to decide the question. So let's mark 1 as insufficient and cross out answer choices D and A. As for statement 2, it tells us that the median of the integers in S is greater than the median of the integers in T. So let's write 2, median S greater than median T. Once again, evaluating the statement will involve looking for examples. And we don't want to reinvent the wheel here, so let's try to base the examples for this new statement on the ones we used for statement 1. For the yes example, let's again say that list T consists of the single number 30. That implies that the sum of T is also 30, and that the median of T is also 30. And now for list S, we have to make sure we obey the various constraints. One of them is that the sum of S has to equal the sum of T. So for S, the sum is also 30. As for the median of S, it has to be bigger than the median of T. The median of T was 30, so let's say that the median of S is maybe 35. And finally, the last constraint is that this is supposed to be a yes example, which means that list S has to have more members than list T. So let's follow what we did with statement 1 and say that list S has 3 members. And by definition, the median is the middle number when you list from low to high, so let's put 35 as our middle number. The high number we can just make another instance of 35, and now we just have to pick our low number. We know that the sum of this list has to be 30, and 35 plus 35 already comes to 70, so to get that total down to 30, we need to make this negative 40, because negative 40 plus 70 equals 30. So that's our yes example. For the no example, we can again follow what we did in statement 1 and say that list S consists of the single number negative 30. This implies that the sum for list S is also negative 30, and that the median is the same, negative 30. For list T, the sum again has to be the same as for list S, so it's going to be negative 30. As for the median of T has to be less than the median of S, which means that this median has to be less than negative 30. So let's say that it's negative 35. And because this is a no example, list T is supposed to have more numbers than list S. So let's say that T has 3 members, and if we list them from low to high, the median will be the middle number, so we can write negative 35 in the middle. Let's pick the low number to be another instance of negative 35. And then to make the sum come out to be negative 30, the high number has to be 40. So now that we found both a no example and a yes example, we know that statement 2 is insufficient. And on our DABC grid, we can eliminate answer choice B. And now that we're down to C versus E, we need to think about the two statements together. In other words, we need to construct a united statement, U, that combines the information in 1 with the information in 2. The way to check whether this combination has enough information to answer the question is again to look for examples. It would be really nice if we could avoid coming up with entirely new examples. So let's see if we can recycle some of the examples that we already have. We're not going to be able to reuse the examples from statement 1. We know this because when we were working on statement 2, we found that the examples from 1 violated the condition that median S is greater than median T, which is why we came up with new examples for statement 2. But let's look at these examples from statement 2. maybe they still obey the requirement from 1 that average S is less than average T. So let's figure out the averages to see if this is true. Here in the yes example, list S has a sum of 30 and has 3 members, so the average is going to be 30 divided by 3 is 10, and list T has a sum of 30 but just 1 member, so the average is 30. As for the no example, the sum of list S is negative 30, and there's just 1 member, so the average is negative 30. And the sum of list T is also negative 30, but there are 3 members, so the average is negative 10. Now 10 is less than 30, and negative 30 is less than negative 10. So as we suspected, these examples obey the demand of statement 1 that average S be less than average T. This means that our examples here obey both statements together, which means that they obey both components of the united statement. Thus, the examples for 2 work for U. And since we now know that U has both a yes example and a no example, we can say that U is insufficient, which means that our final answer is E. Let me wrap this up with a couple of comments. One is that this problem is unusually hard, so hard that when they first put this on GMATPrep, the official answer was incorrect. They gave the answer as A, meaning that statement 1 by itself was sufficient, and then they had to change the answer to E because they realized, oh wait, it's possible to come up with a no example here if you use negative numbers. Now, even though this problem is unusually hard, it illustrates a general truth about solving GMAT problems, which is that constraints are helpful. What I mean by that is that often we have to come up with examples, and it can feel like obeying the various constraints, such as sum S equals sum T, or average S is less than average T, or even yes or no, whether S has more integers than T. All of these are constraints on the examples we can pick. It can seem that obeying all of these constraints at once is overwhelming and difficult. But it's much better to think of it another way. Constraints actually help you create the examples. It's a little bit like another creative endeavor, writing a poem. If I just say, come up with a poem for me in 5 minutes, you might freeze up. But if I say, it has to be about trees and it has to be a haiku, you might be able to do it quite easily. I mean, kindergarten kids do this kind of thing all the time. There's something about constraints, such as 5 syllables, 7 syllables, 5 syllables in a haiku, that actually makes it easier for you to come up with an example. So in these math problems, the constraints, such as the things I've put in green here, are useful as a guide for coming up with these examples. The trick is, of course, to use them step by step. So as we saw, when we came up with our examples, we first did sum S equals sum T, so we picked 30 and 30. Then we ensured that S had more integers than T for the yes case, or fewer for the no case. And then we made sure average S is less than average T. So it's a matter of click, click, click for generating your examples, and this gives you a roadmap for how to solve. Alright, thanks for watching, and I hope you'll like this video and subscribe to this channel. Now, even though this problem is unusually hard, it illustrates a general truth about solving GMAT problems, which is that constraints are helpful. What I mean by that is that often we have to come up with examples, and it can feel like obeying the various constraints, such as sum S equals sum T, or average S is less than average T, or even yes or no, whether S has more integers than T. All of these are constraints on the examples we can pick. it can seem that obeying all of these constraints at once is overwhelming and difficult. But it's much better to think of it another way. Constraints actually help you. It's a little bit like another creative endeavor, writing a poem. If I just say, come up with a poem for me in 5 minutes, you might freeze up. But if I say, it has to be about trees and it has to be a haiku, you might be able to do it quite easily. I mean, kindergarten kids do this kind of thing all the time. There's something about constraints, such as 5 syllables, 7 syllables, 5 syllables in a haiku that actually makes it easier for you to come up with an example. So in these math problems, the constraints, such as the things I put in green here, are useful as a guide for coming up with these examples. The trick is, of course, to use them step by step. So as we saw, when we came up with our examples, we first did sum s equals sum t, so we picked 30 and 30. Then we ensured that s had more integers than t for the yes case, or fewer for the no case. And then we made sure average s is less than average t. So it's a matter of click, click, click for generating your examples, and this gives you a roadmap for how to solve. Alright, thanks for watching, and I hope you'll like this video and subscribe to this channel so that you can get more solutions from Chiron GMAT.